firmware engineering workshop. So that's my favorite subject. Let me see. It is actually just E4. Okay. So in the 1990s, almost 20 years ago, we started put out the E4 model, and then 10 years later, I was, we got the version 2, and now we got version 6. I don't know, I forgot the steps 3, 4, and 5, but we had the version 6 anyway. So I just want to tell you a little bit about what's involved, the latest developments, and particularly 2 projects that I'm working on right now. One is on the EP32, which I brought the board for you to look at it. And another one is the ARM7. I implemented 3 versions of ARM7 E4s on 3 different ARM7 chips. So that's fairly interesting. And I bring in the demo, the digital storage oscilloscope demo, fully working, okay? But it's so small, I don't think anybody can see very much of it. But if you're interested, come over here and take a look. So that's what we want to build is something like this. You put in your pocket, and then you can go out and measure signals. So I will do a little bit demo of this thing. I brought the FPGA kit, but I don't think I have time to do demonstrations. Okay, so that's the summary. E4 model. It is based on. Well, I have the Bill Minch here, right? He's the one who originally donated his model for this project, and it's based on 32 or 30-some machine code primitives. And then based on the 32 primitives, we add in about 120 high-level words. And then it's a full interpreter, compiler with some debugging tools. And the original design was portability. So we wanted to put this on any use for computers. At the time, remember it's 1990. At the time, Intel has pretty much dominated the microprocessor, but there was still lots of very interesting processors coming. So I think this model, at the time we were looking at what will happen in the next 10 or 20 years. And I think we need a very simple force model which can be implemented on any of these newer processors. So we did. In the version 2, in about 2 or 3 years, we collected about 20 different implementations. Many people all over, just took the model and put it on their microprocessor of their fancy, what they are currently working on. And they then mail me back the implementation. So we got a quite good collection. So version 2 is about 2000, and I start to use the E4 at work. So any project I came along, I'll just implement E4 and then go on with the project. So I have encountered many processors and put in the version 2. Version 2 was optimized for whatever the processor, for whatever the application. E4 is optimized for that particular processor and for that particular application. So it was it was quite. I lived off E-Force for about 10 years. And now, okay, version 6. Version 6 is, and then I realized that for the performance, the best implementation for E-Force is the subroutine threading. Okay, so that, and in the version 6, I started to really move everything into subroutine threading, and then because it's in subroutine threading, we can mix assembly code directly with high-level subroutine calls. So that basically flattens the field, and there's no difference between high-level forth and low-level forth. So it allows the force to run at the highest speed. Of course, we also try to move the MUP21 model into real other FPGAs. So I was implemented. I implemented the EP32 on Xilinx, Actel, and Atera FPGAs for various different applications. And the E-Force, of course, when you have a real force engine underneath, E-Force becomes extremely powerful, extremely fast. And unfortunately, you can't sell force chips. So all these things become basically interesting projects, but never get to real chips. So for real chips, it's the ARM7. And now ARM7, there's so many different versions and so much capabilities thrown into the chip that lots of very interesting things can be done on the ARM7. And I have implemented ARM7 E-Force for the Nintendo Game Boy Advance. So that was an interesting project. And then I use analog device ADUC 7020, which is a very powerful microprocessor with very fast A to D converter, among all the other things. And then Atmel SAM7 is also is even more powerful than the analog devices. Interesting thing about it, or the thing that besides all the peripherals that that you have, the interesting thing is that it has 256 kilobytes of flash, and that allows me to with fresh memory on chip, then that makes the firmware production very easy. So you don't need any, almost you don't need any external tools. Everything's in the chip. All you have to do is talk to it, and then you can embed the your application into the chip directly. And this of course comes. This has the best platform for firmware engineering. And firmware engineering, what does firmware engineering mean? It just originally in the early days, it's ROM programming. If you do anything, you program a ROM and stick the ROM on the board, and you power up and get your application going. So that's what we call firmware. And with the with E-Force system, my idea is that you have to have a fully functional E-Force system in the target. Okay, and it doesn't make any sense to save a few thousand bytes because now you have in the ARM7 chip, you have 256 kilobytes of flash. Okay, so that's enough for you to put in the fourth and then your application and everything else you have in mind. The key thing is to use the E4, and you can compile it on the target, develop your application, compile your application. When you're happy with it, you copy the whole dictionary into Flash, and then next time you boot up, your application is right in front of you. So that's the what I want to the whole technique, all the technology in developing a firmware is all embedded in a very simple E4 system. And if you have a platform which gives you the flash memory, then you can very easily develop your application and probably build some nice products. So last night at home I got everything working, okay, but I think it's too much trouble to demonstrate the Atera statics. Yeah, I got everything in here, but this is not a computer that I trust. So every time I bring it up, every time I take it to places, it hicks up. So the board is over here. Okay, and the FPGA getting very hot, so they have to put a fan on top of it. So, but it's this is very nice. Okay, you can I can synthesize the E4. The whole 32-bit microprocessor occupies 5% of the resources on this chip. So I only occupy 5% of the logic, and then you can get lots of different applications or on it. So and this was an application that I worked last year or a year before for NASA. And this board just plugged directly onto the FPGA board, and it got a camera there. So I was able to capture images using this camera, and I also implemented a massively parallel processor because I only use 5% of the resources on the FPGA. So I was using the other 95% of the logic to implement a massively parallel processor array. It's still not big enough for my liking, but it was quite. It was already 128 by 64, so it's a sizable array. If I can get into the newer FPGAs, I probably can get 512 by 512. But the principle is there. We can use the put in lots of logic, many different logics onto the same FPGA, and use the E4 on the EP32 to do the controlling and to do the scheduling. When you have millions of processors working in parallel, you need another processor to do your controlling and interfacing. So that's E4 is very well suited for that particular purpose. Okay, so that's the if you are interested, I can probably get it to work this afternoon. But I'm not ready to demonstrate here. Okay, this is E4 on the RMX board, which is this guy, and Dave gave me this board. Gave me this board 2 years ago, right? And then I finally got to work on it. The most interesting thing of this board is that the 132 by 132 colored LCD on it. So this I tried to use this one to demonstrate the digital storage oscilloscope. So I was able to get almost all the functionalities onto the ARM7 and showing traces on the board. I think I got it to work. I showed the traces about 3 months ago at Stanford. But at the time, the user interface was not polished, not worked out yet. And right now, I have worked out the user interface. On this board, it has a joystick switch. You can see it's a joystick switch which has 4 switches. You can push to the right, to the left, to top and down, and the center there's another switch you can push. So it has this 5-switch joystick, and 2 more switches, 1 on each side. And I wasn't clear in my mind for a long time how to best use this joystick. Okay, and at one time I said, okay, for the oscilloscope, I need to change the traces. I need to change the scale. I need to change the timing. So the joystick, I got up, down, left, right. I can implement all these functions to the switches. But finally, I decide, yeah, it's nice, but they are still limited because you only got 5 or 7 switches, and there are lots of things you can do with 7 switches, but not quite enough for a full-fledged digital storage oscilloscope. The best way I finally figured is that I'll use this joystick to control the menu. Okay, the left, right, up, and down. Just move through the menu system, and when you have selected the proper item on the menus, you push the center button, and it performs the function. So I think that's the best approach. And with the menu system, you are not limited to the functionality that you can create as many menu items on the screen as you wish. And so right now, what this whole thing, I think, booted up, and the menu is already there. If I push the switch to the left, to the right, you can see it's showing one of the 4 different menus. And if I push the up and down button, one of the menu items is highlighted in blue. Okay, so that's what you are selecting. And then if you push the center button, it will just perform that function. Okay. And the most important function of the oscilloscope is, of course, showing the traces. Okay, and it is if you push this button, okay, it into the scope mode, and it's showing traces. Now, if I can get some music. You can see the traces. Well, you can't see, but you're welcome. You're welcome to come over and take a look. So this is the. If you push the other key on the left, it stops and return you to the menu system. So I think that's I wanted to have a dual trace capability. So one trace is shown in red and one trace is shown in green. And of course I have already get the triggering mechanism not working. I have all the code there, but I just don't have enough time to get it working on this thing. Mainly because I can't see now. I got the operation on the right eye, so I can see distance, but not very clearly, and I can't read at all. So it's very hard for me to see things on this little screen, and it's hard for me to read the manuals. So I think, well, I just show you what I have here. Okay, the LCD display, ADC conversion, menu user interfaces. These are the hard part of the project. You know, the ARM7 is very pleasant. So it's and this board is very pleasant. You got everything there. All I have to do is write code, right? And finally, I realized that I'm not a hardware person. I'm a software person. Okay, so I work the best. If you give me hardware, you get all the hardware done. Then I just sit down and figure out all the soft part. But working on hardware, it's and now now I have retired. I can choose what I want to work at, and I have. Basically put all the hardware stuff into garage, into boxes and throw them in the garage. So I got tatami rooms, you know, all the space I have reclaimed. Okay, so I think I got the demo. I won't do any demo on the EP32. If you're interested, you can come and talk to me. And here is the trace. I have to leave the trace going there. Thank you very much. Any questions? Yeah. DFT. Yeah. Yeah. Because I have the DFT code. I have the DFT code.
Really?
Yeah.
FFT is kind of very straightforward.
Nah. FFT. It's not worth it. It's not worth it. Okay. Because
N squared versus log n log.
Yes. You know the reason you use FFT is to optimize it against multiplication.
Right.
Okay. Now the multiplication takes the same time as addition. There's no reason to do FFT. Okay. And the DFT. Well, I did the DFT because actually I proved that in a continuously running DFT situation, errors don't accumulate, even with very limited digital precision. Yeah, you have 8-bit, 12-bit, whatever your A to D gives you. Okay, you take that much bit, take that many bit, do the processing, and you run it continuously for 100 years. Errors don't accumulate. Okay.
If you're doing continuous calculations too, you don't have to worry so much about it also. Right.
Yeah. Right. Yeah. And I think the one thing. Anybody remember Jim Henderson? Yeah. Okay. Yeah. He's the guy who was with the innovative technology. He's still using forth. So he talked to me just last week, asked about the CFT. He said he got that project which and they are digitizing signals at 2 gigahertz, and he need a Fourier transform. I said yes, yes. My system I invented in 1980, and now it's the time is ripe for committed into hardware, okay? Because when you do FFT or any Fourier transform, the sampling rate is the period that you take that many samples. Okay, you take 512 samples. You take all these and you do the Fourier transform, and the sampling speed is the speed that you are taking 512 samples. Okay, you cannot sample any better than. But the continuous Fourier transform, every sample you take in, you do 512 conversions. You get 512 Fourier coefficients, and you are sampling at the rate that you are actually sampling. Okay, so this you cannot beat it. If you can have one processor for each node, then you are converting it at every clock cycle, and every time you do a multiplication add. Okay, and the problem is how can you get all the data out in a useful form? But I think that's the user's worry. Yes.
What's the application for the camera?
For the camera, okay, that's well, supposedly it's called a focal plane. That's a technology, the technical term. And focal plane, that's what they when you fly the instruments into the space, and they sense infrared or visible, UV. And on the focal plane, you have an array of detectors. Okay, and this is what the guy had in mind. He said, well, I want to capture images very fast, and I want to process image very fast. And the way to do it is to have a sensor array, and the sensor array is connected to the your processor array. And each array element is processing 1 pixel all the time. Okay, so that allows you to process the whole image at a very, very high rate. Yes.
Were you doing image correction?
Yeah, we can do everything. Anything. Yeah, and then it's doing every pixel, all the pixels at the same time. Yeah, you can put in the correction table, and you can put in all the selection criteria, all in the processor array.
You can do this like a normal parameter.
Oh yeah. The problem is to get the data into the array and get the result back out.
I can see this with like a full light level.
Yeah.
Like
Oh yeah. Yes. The demonstration for that project is the image averaging. Okay. Yeah. So you just accumulate lots of frames, and then that smooths out the tempo irregularities. Yeah. Okay. All right. Thank you.